this is my presentation for the ISMIR late-breaking demo, a comparative study of transfer learning for drum audio style classification. So we'll look at some related work, and CNNs and transformers are known to handle audio classification quite differently. CNNs are often known to focus more on local features, where transformers look at more global features. And specifically, the AST, the audio spectrogram transformer, which has been further adapted into the patch-out audio spectrogram transformer, is really shows quite the difference in this task. In addition, transfer learning has been shown as a great way of training a model on a target task and then using it for a source task, and it has shown many benefits for many classification tasks. In addition, augmentation and padding have been also employed to enhance generalization in these contexts. So for more details on the context, many studies that involve drum audio style classification or patterns are basically focused more on symbolic representations. This includes studies, for example, in ADT field, the automatic drum transcription field, where classification in drum audio is more focused on single instruments for the drums. So now that leaves us a gap where we can look at drum audio styles, so the semantic labels on top of the patterns, and compare that against a CNN versus a pre-trained transformer-based model, which leads to our research question, which is what is the effect of pre-trained general audio embeddings in past compared to a baseline CNN for drum audio style classification. For our method, we're going to use the GMD, which is one of the largest drum data sets with a lot of regularized files with different tempos, but also primarily these primary and secondary styles tags that are added to each file, which gives us a lot of room to examine how these models are going to handle this audio. For the baseline architecture, we have this fairly simple architecture from Heiner that we will then modify to meet our needs. We also have past here with disentangled time and frequency positional codes. You can see here on the right. We're going to use a lighter version which has 7 layers, and we're going to, in a key detail, we're going to keep the embeddings frozen from audio set. We're not going to do any fine tuning because we want to isolate the effect of what is the relationship between those audio embeddings and the target task, which is drum audio style classification. For augmentations and padding, we're going to be using Gaussian noise, room simulation, time stretch, and time patch-out, which allows us to explore both waveform and spectrogram-based augmentations. From padding modes, we'll do zero padding, circular padding, and reflection padding to see how those will shift the embeddings. So for experiments, first round, we're just looking at a subset of the data with primary rock styles where both perform quite well. The second group of experiments expands more to the full data set where both models are still performing quite well. The third group of experiments then optimizes those two architectures where we look at the MLP, we add layers, we find the right amount of layers, the same thing with the CNN with the convolutional layers. We also look at bottlenecking. The fourth group of experiments and final is then about augmentations and padding, which is you can see some of the best scores. The best scores of the experiments happen here with the CNN and with past. So for confusing matrices, we also noted that jazz, Latin, and folk styles are often confused, but these confusions often revealed primary styles, or clustering between primary styles. And we also noticed that the CNN was more affected by a skew towards the rock class. When we look at the embeddings, a key difference here is you can see on the image on the top right that the CNN is more clustering around individual style classes rather than by primary style, because you can see with the color coding of primary style. In addition, the bottom image shows how the embeddings of the whole model shift per experiment. So it shows that the CNN has a less robust feature representation. It's more prone to shift, and it also has an anomalous cluster that it doesn't know how to deal with exactly. In past, you can now see, by contrast, a much more broadly clustered embedding space by primary style and a much more robust representation per experiment change, except for when padding modes are changed. So it shows that past has a more hierarchical understanding of drum audio style compared to the CNN. So discussion, we basically shown that even though the CNN outperformed past in terms of accuracy, past general audio embeddings seem to create a more robust feature representation. Some limitations were that the rock style was heavily overrepresented in the data set. We did make some changes to make sure each split had proportional balancing, but this was still a limitation. Future research could then incorporate this with a larger data set, other transformer models, ensemble models, or maybe even unsupervised learning contexts. So in conclusion, this is the first comparative study for a CNN baseline compared with a pre-trained transformer-based model for drum audio style classification. And we saw that even though the general audio embeddings reduce accuracy, there still is a robust feature representation in past. Thank you.